Hello. Today we're going to talk about all the conservation law, but not all of them, most of them, or law of conservation. So we have talked about one, mass conservation. So this is true, except when you, let's say you in a very high temperature, okay, like temperature. So this means temperature is larger than, let's say, just for example, right, like a 6,000 degrees C, for example. That's one condition. And there may be other situations, okay? So that's one of the conditions. So let's say in the sun, right? In the sun, mass, right? In the sun, mass can actually become energy. So mass is no longer conserved, okay? And energy can also become sun and become mass. Energy can also itself can become mass. So that's no longer true in this kind of exceptional condition. So mass conservation is almost always true. Okay? So that's why when we say delta mv, right, like a momentum, then m usually come out and v stay inside. Okay? So v can change, but mass doesn't change in our example, right? A lot of times. Number two, energy conservation. So this energy is a general term. General term. So we're talking about energy. What energy we're talking about? So basically, you're talking about including, right? Including the heat energy, right? The potential energy, the kinetic energy, right? You put them together, mechanical energy, and then you have here your spring potential energy, right? You have gravitational potential energy, you have electrical potential energy, right? You have sun energy, right? You have light energy. So the light itself, right, can also have energy, right? And you have solar energy, which is one of the lights, right? And you have nuclear energy, right? Chemical energy, right? So there are many, many different kind of energy. So this energy that we're referring to is talking about all types of energy, right? So this is almost always true, except, right? Except like in the sun, and there may be other conditions that I'm not aware of at this moment, right? But if I go do research, there may be other situations like in the sun that this energy conservation no longer true. Energy itself can turns into mass, so energy can actually reduce. Okay, all right. So number three, we talk about mechanical energy conservation. So this is true when you don't dissipate the mechanical energy, right? Obviously, dissipate. Dissipate means 消耗, right? In Chinese. Okay? If you don't dissipate, right? And this usually involves friction, drag, right? Okay? So dissipative forces. So if you don't dissipate the mechanical energy, then this will be conserved. So it's not always true, right? If you have friction, then your mechanical energy may go away. All right? So I'm going to erase this. Okay. So obviously the mechanical energy conservation is not true if I have this, have a mass, and then I have friction down there, right, is equal to mu n. Then let's say it has the kinetic energy. And after some time, then it will come to a stop, right? So you know mechanical energy did not conserve. Okay, so that's number 4. Momentum conservation. Okay, so this we referring to linear, right? Because later we'll study angular momentum conservation also. So this is linear, right? So this is the Pi equal to Pf, right? So when is this true, right? As long as your external, right, your net force, right, external net force is equal to 0, then your momentum will be conserved. Okay, so let's say if I have the system just like a mass like this, and you have friction here, mu is not equal to 0, so then I have my P here. This is not conserved because I have friction, so I have external force in the direction that my momentum is, right, in the direction of P, right? So the net force we're talking about is in the direction of P, same direction. So in this case, I have my force, friction force going this way, right? So in this direction, so my net force external, right, it's equal to friction, which is going to the left. And my P is going to right. And the both are in the x-axis, right? The both are in the x-axis. So it's not going to be conserved. So keep in mind, you need to have this for this to be true. So that's number 4. And number 5, kinetic energy conservation. So this is even less often, right? So for example, if I bounce a ball, right? So when this one reach here, this one here has a velocity right before it touch, right? Has a velocity v. But when it bounce back, this one here maybe bounce back with a v, v prime equal to 1/2 v, for example. So this is less than the original v now. So you know your kinetic energy is not conserved, right? So this is true when you have a so-called elastic collision, right? In Chinese, this is called 弹性碰撞. It's just a name, right? 碰撞, okay? All right, so for example, if I have this, I'll give you another example. So let's say this is V and this is V, right? So after they collide, if this one goes out, this one here become 1/2 of a V. And this one here goes out with 1/2 of a V. Then you know this kinetic energy was 1/2 mv squared times 2. And in the end, you only have 1/2 m, and this v squared become v squared divided by 4 times 2. So obviously you lost your kinetic energy. So this is not an elastic collision. This is inelastic collision, right? So elastic collision, all right? So that's the kinetic energy conservation. The last one, which we don't deal with too much here, but we still have more, right? But I'm just going to talk a little bit about charge conservation. So what do you mean by charge? Charge means positive charge, negative charge, right? So example like this is like proton inside the nucleus, right? This is inside nucleus. So 原子核 in Chinese. 核. Okay? So all like ion, right? Positive ion, right? For example, H plus, hydrogen, right? Plus. And negative, this is like electron, okay? Or negative ion, right? So like, for example, O, -2, for example. So charge conservation means that the charge, right? If you have, like you have, let's say you have an H, and then you have O, so 2H, right? So you have O, okay? And this one has how many charge? So how many negative charge and how many positive charge? And this one has how many negative charge, how many positive charge? And they are neutral, right? They are atoms, so they are neutral to begin with. Neutral, Neutral, 中性的, so means your positive and negative are the same. So when they do chemical reaction, still your positive and negative charge doesn't go away. You add them together, the number of charges, the number, this means the number of positive and negative charges, right, remain the same. Okay, and that's the charge conservation. So I'm not aware of any exception. Maybe in the sun, this one can also change. Okay. All right, so I'm going to stop here for the conservation law. And so, but keep in mind, conservation law, it's the foundation of physics. So the proper name is the laws of conservation, right? This is the foundation, or at least one of the bigger foundation for physics. Okay, so this law, in my opinion, is bigger than, right? Say, for example, Newton's law, right? Of course, you know, this is probably worth debating, right? And then, for example, like Kepler's law. But you know, these are related. This can be related back to the conservation, right? But we haven't talked about that yet. And for example, UGL, right? Universal gravitational law. So universal gravitational law. Right? All these other law, like Ohm's law, right? Which is in the electricity, Ohm's law. Now this is even smaller. This is even smaller than this three law, right? These three law are bigger, right? The impact or the extent of it. These are universal law, right? They are called universal law. But this is an empirical law. So it's based on experiment, right? And it cannot be applied everywhere. Cannot be applied everywhere. Only for certain material, right? And there are more laws, you know, there are more laws here that is not the laws of conservation, but here is the laws of, you know, of other law that we studied before. Yeah. So in my opinion, this is the foundation of the physics. So that's the point. Of course, this is also the foundation of physics. This is also the core, right? This is also, right? Because these three laws are very big, right? Very fundamental. All right, I'm going to stop there. Hopefully you learned something about conservation. And